we'll go ahead and get started. So welcome to the 19th session of EE 7391. So thank you very much for coming. We've got some audience members. Appreciate you coming. For those who are watching this on video, we appreciate you watching. Wanted to continue on in our discussion about multi-layer neural networks. And one of the things that actually I'm, let's see if we're in a new room here. Let's do this. One of the things actually that that's important that I'm doing is actually defining the notation for neural networks and how to basically adapt them in the context of, in this case, what we've been using before, which is adaptive filters. Because if you read about neural networks, you're probably aware that, yeah, the equations are very simple, but indices get left off, right? So a lot of times, you know, it's not clear exactly, for example, if there's a sum to do, you have to add across something. It's not clear what to add across. Sometimes it can be challenging. And it's easy to actually get bugs. It's actually easy in that context to write code that kind of is right, but has some bugs in it. And of course, because the algorithms are adaptive, you don't see the bugs, right? You don't actually see the problems because the system kind of works. It's kind of adapting to create a solution for you. So you might only catch this later when you actually try some different cases. So that's one of the things that we're definitely doing. And of course, we're also going through and figuring out, we're going to not just define the algorithms, but then start looking at a lot of the choices with respect to the algorithms, which is another important piece of the overall problem. So in our notation, we have sort of n, which is, of course, that's associated with this pair y of n and x of n. This is input. And this is, if you will, the desired signal or the training signal, right? Call it either one. And really refers to the pattern index. And then we have k, which is associated with the w, you know, wm sub k. This refers to essentially the weight index, actually I should sort of weight iteration index. And then of course there's m, which is the layer number, right? That's the idea. So those are the things. And then of course we also have the size of this guy. This is actually, if you will, L by m plus 1 by Lm. This is actually the number of inputs, and this is the number of outputs for that particular layer, right? And by the way, there's also, when we talk about m, there's those, and so if you will, the layer number, we're going to have an associated quantity, you know, fm of d hat, right? And this refers to, of course, the nonlinearity in the structure at layer m, right? So you get the idea that we're actually defining all of these indices, and in terms of neural network training, and then we also have sort of capital M, I guess maybe I'll write that over here. Capital M is the number of layers. So in our neural network training example, we're going to set, in our example, m is equal to 4. And so what that means is we have an input layer. We have 3 hidden layers. And then we have an output layer. Now I know you're looking at this and you're saying, well, if I count this, I actually have 1, 2, 3, 4, 5, so what's going on? Why is it that I'm saying I have m equal to 4, I have 4 layers? Well, the way to think of it is, between each one of these layers, there's a set of weights, right? There's a w of m of k, oh, and I guess I'd say there's a b m of k as well, the bias weights, the bias weight vector. So this actually refers to the number of sort of WMK, BMK sets, right? That's what we're talking about. And in fact, it also refers to the number of nonlinearities. Also, the Fm of d hat is also something there, right? That's what we have. So, so if you will, the way to think of it is, okay, there's not really, between the layers is where we have the weights. And so, we think of it as 4 basically weight sets when we talk about the structure. And you can either think of it as input layer and 3 hidden layers, or 3 hidden layers and an output layer. I think typically people don't refer to the input layer as much as the output layer. So, the hidden layers and the output layer all have nonlinearities associated with them. So that's the reason why we kind of associate that as a 4-layer structure. And of course, at the nth layer, we have this output, which we're going to call y hat, which is a vector of n comma k is equal to f of m. And then we have wm of k times the input pattern, which I'm going to say, if this is at the nth layer, it's going to be xm of n. And by the way, I'm suppressing, there's really a hidden k here. And the reason why, because if you will, we're going to set xm of n to be y hat of m minus 1 nk, right? But this depends on previous, w, sort of lk, L less than M. So from the standpoint of a cost function, gradients, that sort of thing, it doesn't enter in. That's the reason why we can get away with suppressing that, at least at this point. And then I have Bm of K, okay? So that's my resulting notation for the nth layer output, right? That's what I'm calling this particular output. And so, and then of course we talked about cost functions. And the example I'm going to use here is basically sum of squared error. And the sum of squared errors, of course, is j of k is equal to the sum over n from 1 to capital N. Capital N is the number of patterns. J of, in this case, nk, where the individual j of nk is, I'm going to say E of n, and I guess we'll say n comma k to transpose E of nk, where E is just the y of n, this desired or training signal, minus y, and in this case it's y4 hat of nk, which of course is the last layer output. Right? So that's what we do, and so that's the resulting cost. And if you recall last time, we had gotten to the idea that the update is equal to Wm of, well, actually, we were only talking about the 4th layer at this point. Update for, if you will, F4 of D equal to D. Then we had actually worked out, in that context, what it was going to be. It was going to be basically W4 of k plus 1 gets W4 of k. Of course, it's minus some mu times the derivative of j with respect to W4 of k. And of course, this is going to be the sum, the average of the derivative of the jnks with respect to W4k. And then, is where we are, j of nk with respect to W4k is equal to, and we had just said ei xj. Well, I had motivated that makes it E of n comma k times x, in this case 4 transpose of n. That's what that is, that particular outer product. Actually, and there's a minus sign there because there's a negative. And this should look familiar. This should look like, this is basically LMS, right? When we see that, we see the error times the data. And now granted, it's an outer product, and there's a transpose involved. That's the reason there's a transpose is because there's no transpose here. So if you will, there's not transpose. So as it were, we have a transpose. So that has to happen, or happens to happen here, with respect to this. So that's the reason why that shows up. But otherwise, and of course, this is a vector because it's a multi-channel error as opposed to a single error. But otherwise, it's basically like LMS, okay? Now, what happens when we have a general f for D is not linear? So what happens when that happens, if you have that? Well, it turns out it's basically the same thing, and actually I think I had 1/2 of this. One half of the derivative of kind of this E transpose E with respect to 4 is equal to, in this case, and this is the ijth element, we get EI, and then we get the derivative of the, if you will, the ith output from that system times xj, okay? And so what that causes that to mean is that if we take 1/2 the derivative of j and k, what we end up having is a change with respect to the relation. The change is we have a diagonal matrix of f4 prime d1, d1 4, and this again, this would be nk if we want to write it out, right? All those things. f4 prime of d2 hat for nk, all the way down to f4 prime of d, in this case it's L, it's actually L5. There's actually, if you will, and that's the other thing to recognize is that if I go back up here, input layer has size L1. These have L2, L3, and L4, and then there's an output layer of L5, right? So if you think of the first layer as having a dimension, then obviously the output layer has one additional dimension beyond the 4 sets of weights. So this is DL5, 4, and this is NK, and then there's zeros there, zeros there. Otherwise, there's still the E, NK, there's still the X4 transpose N. So it's still that. So this is a diagonal matrix of derivatives. And this is really sort of output derivatives, right? And we're going to call this matrix capital F 4 prime of D for NK, right? And there's actually a hat there, right? So the way I think of it is just evaluate it this way. Now, would you implement it this way? Well, probably not, because all you need to do is find E and then multiply every element, the first element by that, second element by that, third element, so on. So you wouldn't implement it like this, because this adds complexity and multiplying by zeros that you don't need. But notationally, it's very nice, right? Because it enables us to kind of grab the resulting relationships with respect to the system. So that means then that the derivative of j of k with respect to the weights can now be written as negative 1, and this is 1/2 again, negative 1 over n sum n from 1 to capital N of f4 prime d for nk, that's a hat, that's the output, times E and K, and then I have X4 transpose N, which of course this is Y hat 3 of NK, right? Transpose, that's what that is. And so that means then that we actually can now write the, we could write the update. We could basically now update the coefficients. We have this, so now we could say W4K plus 1 is equal to W4K, minus 1/2. Actually, we need a step size in there. So minus mu over 2 dj of k dw4 of k. So we could actually compute this and do this and go on. Now, we want to talk about the third layer. So if you will, m is equal to 3. then what I want to do is I want to calculate the derivative of j of k, so my original cost, with respect to the third set of weights, which of course is 1 over n. Again, I'll do my 1/2, and it's negative 1/2. Actually, no, I'm not going to have the negative yet. I'm going to have the 1/2, and then the 1 over n, and then the sum from n, from 1 to capital N, that's the input pattern. And then I'm going to have the sum, in this case, from L, from 1 to L4, because this is my cost, and I'm taking the derivative of E of L squared of NK. So this is my, my error, right? The output at the error, because I don't have errors at individual layers. I just have errors at the output with respect to W3 of K. So I want to compute this, okay? Now, what I end up doing, of course, is having to take this derivative. Now, what do I use? I use the chain rule of calculus to be able to implement this. And so 1/2 of the derivative of just the scalar term, the Lth error, if I do this with respect to the weights of the third layer, ij, well, I still have the same derivative as I had before, right? I still have the negative ELNK. I still have F4 prime D hat of L4NK, so I still have that. And then I take the derivative, so if you will, this is the derivative of the Lth error. This is the derivative of the output associated with that Lth error at the fourth layer. And now I'm going to take the derivative of D hat of L4 and K with respect to W3 of K, I, J, right? So that's what I've done, is I've actually, if you will, used the chain rule and said we'll take the derivative with respect to the error. And that has, if you will, a y minus a y hat. And then I have to take the derivative of the output that produced the y hat. And now I'm into the next value that's in that resulting chain of derivatives, which is the derivative of the fourth output with respect to, in this case, the linear output. Remember, D4 of NK is equal to W3 of K times X3 of N plus B3 of K, right? That's that. So I'm able now to evaluate this. I can push this all the way back. Now, what this means is that I can now look at the Lth position of this DL4. So I have this D hat L4. I have this vector. And that's equal to, if you will, my W. Well, actually, this is the interesting thing. What is this DL4 equal to? Actually, I'm sorry. I got an issue. Let me go back. The DL4 is actually 4. I apologize. It's W4. We haven't gone back yet. Getting ahead of myself. So W4, and actually this is 4 NK BK. So DL4 is, in this case, W4 K. And then what I'm doing, of course, is I'm multiplying by X4. What is X4? Well, let me move this down. Just a moment. I need this space. My X4 of N, of course, is Y3 hat of N comma K, and this is a function of W3 K, right? That's what I want to be able to work out. So if I look at my DL4, then it's actually, and by the way, this then is equal to function 3 of W3 of K, X3 of N plus B3 of K, right? So there's where my dependence on W3 is. So if I look at DL4, actually let me not worry about the let me not worry about that. I'm going to say D4. I have W4 here. I then have times F3, this is my X, 4 of N, F3 of W3 of K times X3 of N plus B3 of K. So I'm just substituting that in, right? And of course I have plus B4 of K over here too. I'm not going to worry about that right now. And this is NK. So now I have everything I need, right? This is W4, I have the nonlinearity, I have that, it all matches up. That's my D4 defined, that's my X4, Y3. I have everything visible. So now what I do is I look at the Lth position here. So I'm going to draw that out there. And then I'm going to have sort of the Lth position, so L here, and then I'm going to have the Ith position here. So I want to get that. So that's going to be sort of this guy. And then here I have this whole vector, which actually doesn't have any positions. This whole thing depends upon all these values, right? Now remember, what am I after? This guy here is D hat of L4, right? So this is telling me my dependence. This is telling me it's going to depend on this guy, which obviously is W4K, but it's the L-ith position there. And then this depends upon, all of these guys, or I should say it depends on the ith position. Maybe I should do that there. It's going to depend upon kind of the ith position of this whole vector here. Right? That's the dependence I get. But the key thing to recognize is that the derivative of this is as before, right? But for m equals to 3, the third layer instead, right? So my calculations I did before apply here, just with one index down. So the end result of this means I have to deal with these weights, and I have to deal with a derivative that's moved down, and I have to include the effect of these derivatives that I have over here, right? The EL and the F4 prime. And the end result is, when I consider that, is I have to actually use the W4 weights to compute the gradient for the third layer. So the result is the derivative of E transpose NK, E NK over, with respect to W3 of K, that's going to equal, actually starting over here, it's going to equal E NK times X transpose 3N, that's going to show up. And then I'm going to have F4 prime of D4 and K, that evaluation, right, that diagonal matrix. Then the effect of this is to have a matrix W4 transpose of K show up, right? Because I have that term, that linear term showing up in my derivative. And then I'm going to have an F3 prime of D3 hat and K show up, just like I did before. And then, of course, the X3 transpose shows up at the very end because that's the derivative that I get when I'm evaluating the derivative with respect to the input-output calculation. So now I can move this over there. So that's my resulting algorithm. I have to take my E, and the thing to recognize is there's kind of a piece over here which is propagating kind of this way. The computation is this way. I start out with E, then I multiply by a diagonal matrix, then I multiply by W4 transpose, then I multiply by a diagonal matrix with a different set. I mean, it's a different diagonal matrix because it's different nonlinearity, and it's a different set of outputs evaluated there too, okay? So that's my resulting gradient, and of course my input is this way. Now what happens at the second layer? Well, at the second layer, basically the same thing happens again. We're kind of at the point where we can say, oh yeah, we can see what the pattern's going to look like. The derivative of the errors with respect to W2, this is going to equal, and by the way, I guess there's a minus sign there too, because we've got the minus sign all the way up the top here, there. So I've got that. Here we're going to have minus, there's going to be F2 prime D2 hat times the W, in this case it's W3, the next layer's weights, F3 prime D3 hat times W4, and then F4 prime D4 hat, and then finally the error times X2 transpose. And again, X3n, this is Y2nk transpose. This here is Y1nk transpose, and so on. So we can do that. Notice that this is here, so clearly we don't want to redo the work, right? So all we're doing is every time, you know, if you will, we copy this over and then we don't have to redo it, and then we just do this calculation here. Okay? And by the way, this algorithm has a name, or this process is called backpropagation. And the great thing about seeing it in this form is that you're seeing all the computations. All the computations are now visible to you. You don't have to think about necessarily indices or what to sum over. This is the resulting update that you end up formulating. And in fact, we could write it for a general M if we wanted to, which is, you know, kind of what does the algorithm look like? Well, we can now write it in all its glory. We have Wm of k plus 1. This is for the mth layer. W of n k plus 1 is equal to Wm of k, just like, you know, what we normally do in LMS, plus mu over n. We have the sum over the data. And then what we have is a product series. The way to think of it is L from M to capital M of FL prime of D hat L n k times W L plus 1 transpose of k. And that product series is done in order, right? Sort of the first, the second, the third, and the fourth, and so on. Or sorry, the mth, the m plus 1th, and so on. And this value is capital M. Now this works out, what we're assuming, and by the way, these are diagonal matrices. What we are assuming is that actually Wm plus 1, which isn't defined, right? There is no fifth layer of weights of k. We'll call that identity, right? We basically, that way, because if you go back, you know, the very first error, if you go back to this, there is no, there is no set of weights applied here, right? But the way to think of it is, you know, I could put a diagonal set of weights, which are just identities, and then that actually work out. So that would allow this notation to actually work. And then this is times E n k, and then we have y hat of m minus 1 of n comma k transpose, where, so we would say, you know, where Wm k, n plus 1 k is equal to identity, and then the other thing is y of 0 and k is just the input pattern, okay? And of course, you know, f L prime of dl hat of nk is just a diagonal matrix of these, of the derivatives of the nonlinearities evaluated by d l m and k. And then of course we have to say what y hat m, nk is. At the mth layer, we have nk is equal to f of m, wmk, y hat m minus 1, nk, plus bmk. That's what that is. And then this quantity is the vector d m hat n k. So that's the whole algorithm. I mean, you're now seeing it in these equations. Oh, I should say we have to define the error. E of nk is just the output, the desired pattern minus y capital M hat of nk. Okay? So that's the resulting algorithm. But I know you're saying, wait a second, what about Bm of k? We have to update the bias weights too, right? The bias weights have to be updated. Well, it turns out that the bias weights, the answer for that's pretty straightforward. The bias weights are basically like inputs with a input value of 1, right? So we can think of the value that we're updating for x, we're using for x as the input is just 1. So it's just the gradient term, plus mu over n. I have everything else. Basically, all these guys copy over. So I literally can copy it. In fact, I'll copy this whole thing. This guy copies over. Copy. And in fact, I think I got everything. I can even erase this guy and paste it. Oh, lasso select. Let's say insert. Actually, just a moment. I'm going to do this. There we go. No. I copied it. Well, maybe I'll do this again. I guess I have to select it and then move it. I may have to redraw, but we'll see. Copy. There we go. If I don't do anything, now I can get it. Paste. So now I have this. So that is what the resulting weight is. And sure enough, I just do that. In other words, I just have a 1 over here. So that's the resulting update. So I've actually already updated or shown what the weights for the bias are updated as. So that's the overall algorithm. And like I said, it involves this computation, which is going backwards, which basically denotes this backpropagation. So the computing of the output, basically the computing of the layers, the YMs building up, is a forward propagation step, and then the gradients are a backward propagation step. Okay? All right. Actually, this is a good pause point. We're about halfway through this particular extended lecture, so we'll go ahead and pause here for about 5 minutes and then come back and talk more about this architecture as well as a lot of the design choices, because that's the thing. When it comes down to it, you've got a lot of design issues associated with this algorithm. So let's go ahead and we will take a break. Put that here. All right. Back in 5 minutes.
So the L is the index of what?
Yeah, the L. Actually, it is the number. It's the length of the weights, right? The weight vector. So the way I think of it is, it's defining the size of W, right?
Oh yeah.
Right. So L2 by L1 is the size of the first weight matrix. So L is like, think of L as like the length of the input signal vector in the adaptive filter side.
It's like the links from one layer of neuron to the rest of us to the other layers.
Well, actually, it's more along the lines of L1 defines the length of the input vector x. L2 defines the length of the input vector to the second layer. L3 defines the length of the vector to the third layer, and so on.
Okay.
Yeah. So that's the notation for that. And there's an L5 because there's an output. And actually, the way I think of it is L2 is the output of is the length of the output for the first layer. L3 is the length of the output for the second layer. So you go down by 1, right, to get those.
And for those structures with different size of neurons on each layer, then the n will be different. I mean, you cannot use a capital N for each because you use a.
What do you mean capital N for each?
Like
No, the capital N is the number of patterns. So that stays the same for all. Capital N does. I'm not sure if you say N.
I saw you omit like Wn. The N denotes the weight for each neuron.
Let me take a look. Make sure I'm. No. W4. Actually, W4 of K. K refers obviously to the iteration index. I've been talking about indices like L and I, which are like pointing to the Lth I element. of that weight. But n refers to the pattern index, small n.
Okay.
Large N refers to the number of patterns, right? Because we have the number of patterns too, right? When we're training the system, we've got, I don't know, however many examples we're going to use to train with. That's the capital N.
Professor?
Yes.
I have a problem
Uh-huh.
about this question. Why here the W can be zero vector? Why the step size is zero? It's not zero. I think it should be zero.
No, because you always, because if your step size were 0, then the stationary point, you wouldn't have a stationary point. The algorithm wouldn't move. So the step size has to be non-zero in order for the algorithm to actually change, to actually have weights which are different, which are converging, or which are moving.
If Wn is always zero, then
It's not always 0.
not always.
No. What's happening is, so the way to think of this algorithm is that we start out with some set of weights, right? And the weights could be anything. And then what we end up doing is we iterate on this algorithm. So there's initial W0, which can be anything. It doesn't have to be 0. And then we iterate this procedure with an arbitrary starting point. And no matter what initial set of weights we have, we converge to a 0 vector.
Oh, okay.
That's what this means. That's what this particular question is asking. If you start from an arbitrary point, or let's say you have been adapting for a while and your weights are something but we can't tell what they are. Where is it that they're heading to? That's what this algorithm. That's what
the
this.
first step is maybe not equal to 0.
Correct.
Okay.
Yes, correct. And that's what I said. The weights are generally arbitrary. You don't have control. Well, sorry, you do have control over them, but you don't always initialize them to 0. Okay, because that would constrain the resulting outputs in a particular way.
Okay.
Yeah.
Okay. Another thing is, for this question, the full point is 15, but you write down.
Yeah. You know what? Actually, you're right. There is that issue there. So I'll that I can adjust. Yeah, you're right. I think I was grading something else. So I think that's going to change the resulting output. It'll be 13 instead of 8.
Okay.
Yes, you're right. So I'll make sure that change happens. Why don't you leave that with me if that's okay?
Okay.
Yeah. All right.
Thank you.
Yep. Okay. All right, let's go ahead and continue. So what I wanted to do is talk a little bit more about sort of why the name backprop and actually give you some nomenclature there, at least from the standpoint of understanding how the computation is being done within the algorithm, and then also make a mention of kind of one of the things that's implicit here in terms of the gradient calculation, which may not necessarily be obvious in looking at it from maybe more general cost functions. So the question is, why the name backpropagation? Or sometimes called backprop. We'll see, it's actually been common enough used that people kind of say, oh yeah, that's, let's call it backprop. Actually, and maybe I'll say something else too. You know, this only enters into, if you will, well actually, maybe I won't worry about that quite yet. I'll make a mention of an issue because it does kind of show up when you start looking at the code of this. Let's talk about the steps. Well, we have a step 1, which we could call basically compute outputs, which are kind of ym. We really want to get to ym of nk. And so what we have is, a typical picture that we have here is we have a set of outputs, maybe 2 outputs, and we're going to have, you know, back from that, we could have layers which have different numbers of nodes, and then we have this, maybe here, and then this here. And so what we're going to say is that this is our input layer. It has x of n on it. And then there's a connection from every one of these samples to every one of the values that are being computed at the next layer. So this set of interconnections refers to W1 of k. And so if you will, this is the first layer, so sort of you know, that dimension, this dimension here is L1. And then at the second layer, the first hidden layer, as it were, I should say it's m equal to 2 for this, but this is W1. Then this is going to be Y1 of nk hat is equal to F1 of W1 of k x of n plus B1 of k. And this we're going to set as x2 of n, and then go on, and then those, again, impact all of these, right? And so on. And then, we forgot that one, and then this is, if you will, so the way I think of it, maybe the best way to think of it is, this is kind of m equal to 1, this here is m equal to 2, and so on, all the way up. There's going to be a W2 of k here, then we connect here. This is the W3 of k, and then here, this is the W4 of k. So there's our 4-layer system. And these outputs that are coming out here, of course, are Y4 of nk hat, which we're computing, right? So we first compute this, and the thing to recognize is that we're doing, if you will, a forward propagation. Forward propagation of outputs to basically, say forward propagation of outputs. Here we're actually saying it's up, right? We're actually going up. So that's step 1. Step 2 is we're going to take errors which are kind of E of nk, or more generally, gradient of cost function terms, right? Because it may not necessarily be errors. It happens to be in a lot of cases that we generate things which have errors. But you know, if we have a cost function which is arbitrary, then it would be some sort of derivative with respect to that cost function. It's still going to look kind of like errors, but it may not necessarily be a pure subtraction, right? That's the thing to recognize. is that it doesn't have to be a subtraction all the time, and propagate them downward. I should say propagate them backward, right, which is our back prop, down through the network. So the idea here is, and the reason why I wanted to draw this guy is, I'm not going to draw the whole thing again in terms of all the interconnections, but I'll draw at least the nodes, and then I'll kind of outline it that way. What's happening is we have kind of an E of nk, and then what happens is we're going to multiply that by a W4 transpose of k, right? And then, of course, we have some nonlinearities, right? We have the resulting f, right, up here. We know if we're looking at the third layer, we're going to multiply, actually we multiply f4. So the way to think of it is we actually have an E4nk, which has some f prime 4 multiplying the E of k, right, E and k. And then we multiply by W4 transpose, and that's going to give us then, you know, a vector here, and then we multiply by W3k transpose, and that's going to give us the vector here, and then we multiply, and of course we have the f's too. So we're going to have the F3 prime, we're going to have the F2 prime, and so on. So this is getting propagated backwards. So this is going this way, right? And we need basically Wm transpose of k to propagate errors. And by the way, it's transpose because it's got to reverse the order, right? I mean, we're going from output to input. So when you go from input to output, it's W. When you go from output to input, it's W transpose. And the dimensions work out. That's the beauty of this, is that the resulting dimensions, it's still a linear relationship. It's just, you know, a linear relationship in the other way, okay? And in fact, we can talk about E, M, and K, that's equal to, that's kind of the error. So we don't explicitly compute, if you will, a difference as an error at every layer, but there is an error associated with every layer, right? There is an error associated with every layer, which of course is this product series. And as we've described it, and times WL plus 1 transpose of K, and this is all times E of NK. So the transpose is important. That's the reason why we mention it. And of course, the question is, does it work? Of course, the answer is yes, it does. And in fact, that's kind of the reason why. I mean, it seems to be a very robust method to be able to do modeling of general nonlinear behaviors. And that's kind of what I want to get into now in the overall understanding of design issues of these systems. Design issues in feed-forward neural networks. And probably the biggest one is the number of layers. I mean, that's the thing that we don't generally have a choice of in adaptive filters, because adaptive filters, we got one layer, right? We got one set of coefficients. You can choose the length of the filter, but otherwise we don't really have the issue of how many layers, because we don't have a layered structure. So the question is, how many layers to use? Actually, maybe I'll kind of, to denote some differences here, I'll have a box. One. How many layers to use, okay? Well, here's the thing. For some functions, and you might argue it's actually quite a large set, where I'm going from x of n, some arbitrary function, to a just scalar y of n, scalar, m equal to 2 layers is enough. That is, I only need 2 layers. And in fact, this leads us to a statement that was actually made a number of years ago, actually approaching 30 years now, the universal approximation theorem. And this is due to a couple of fellows, Sybenko in 1989, and then further Hornick in 1991. What we're going to do is we're going to do the following. We're going to say let f of d hat be non-constant, so it's not flat anywhere, bounded, so it doesn't grow arbitrarily, it basically stops at some point, and continuous. So there's no breaks in it. Now, a lot of functions behave this way, right? I mean, an example of this would be sigmoid would work, tangent would work. Interestingly enough, ReLU would not, okay? Why? Because it's not bounded, right? I mean, it keeps on growing, so we'd have to bound it somehow. So we'd have to change ReLU. But you could think of a bounding there. You'd say, okay, well, let me saturate the ReLU somehow. And define the output. And this is how I'm going to define my output. So just talking about scalar functions of vector inputs. Y is equal to the sum, in this case, we'll say I from 1 to L2 of W2I f, there's my function, of vector W1I transpose X plus B1I, which I could write as, if I wanted to, Y is equal to W2 transpose, which is a vector, times F of W1, which is a matrix, times X plus B, which is a vector, right? I could write it that way. Maybe I'll say B1, okay? This is M is equal to 2 layer with F2 of D just being D, right? In other words, the output, function is linear, okay? Then the theorem says there exists basically a choice of L2, W2, W1 values such that for some, such that, and I've already specified my L2. I said there's a value there. And by the way, these all have to exist, and obviously L2 has to be finite, such that if I were to look at the relationship between, and I think of this as some overall function f of x, if I look at the relationship between f of x minus some other g of x that I want to model, okay, this, for all places in x, is less than epsilon, where epsilon is greater than 0. It's any epsilon greater than 0 for any function gx, and again such, and I want to constrain it too. It's a continuous function such that basically I bound gx, the output of g of x, between 0 and 1. So I kind of constrain it. I bounded inputs, bounded outputs, okay? So it means that a 2-layer system will solve the problem, right? I only need 2 layers, okay? So you might ask the question, well, why go to more layers? Why bother with more layers if I can do an approximation with this? Well, the thing is, they don't really tell you L2, okay? Obviously, L1's defined by the number of inputs you have. They don't tell you what L2 is. L2 could be huge, right? It could be thousands, it could be millions. It's not really clear how big that has to be with respect to a particular function. And so, the the issue is, for some functions, 2 layers is enough, but in practice, the ability of a multi-layer neural network basically to model basically x of n to y of n depends on many factors. Many factors beyond, m, basically the number of layers. So basically the way to think of it is it's a joint design problem which essentially is both an architecture and algorithm issue, or I should say there's both architecture and algorithm issues that we want to consider. So what we don't want to do is simply say, well, let's assume that it's 2 layers and then try to find an answer. The answer can actually be rather tricky to figure out because it may involve a lot of computation if we just limit it to 2 layers. And we want to open it up because we have the capability to go to more layers, for example, and to nonlinearities which are beyond just linear at the output, right, in terms of an approximation. And in fact, I want to talk about that next issue now, which is how to choose the nonlinearities, because this is kind of the next, and of course it's F1. I mean, I don't have just one nonlinearity. I have, at every layer, I've got a nonlinearity up to FMD. Well, for FMD, it turns out for the output nonlinearity, this Fm of D is chosen based on the cost function, so how J of k is defined, and or the data distributions. Particularly, if you think of it as P y of n, kind of what is this data distribution? Because that matters a lot in terms of how you choose this. And you might think, that's really what I'm trying to match. What I want to do is I want to have the system try to match y of n in some way. And so knowing what y of n looks like as a distribution, i.e. a histogram, will tell us a lot about what it is that we're trying to get the neural network to do. And that's something that people have recognized for a long time. And we actually have an example of that you're working on, which is assignment 5, problem 4, right? That's actually the software problem that the simulation problem that you're doing. And if you recall, have that pulled up, that is here, right? So you're doing this problem, and notice that you have a 2-layer system. Notice that we didn't choose a linear function here. F2 is not linear, it's actually nonlinear. And in fact, in the code, I said that you should choose, tangent h of d. So hyperbolic tangent. Well, obviously, that's going to mean that you're trying to model a y which goes between -1 and 1, because that's what an hyperbolic tangent does. You might say, well, why make that choice, right? It seems like we were able to do things with a linear system before, right? This is sort of a repeat of the problem in assignment 2, where you had a linear system and you were able to do some modeling. Why is it that we're using a nonlinear system here? Well, there's a good reason why we actually want to choose a nonlinearity here, and it has to do with kind of the densities associated with the outputs. Now, what I did here is, I'll show this up. What I did was I took actually all the data that you're using. So every student's desired signal, right? Every student's D, if you will. And I did the histogram of it, right? Now, I know what you're thinking. You're thinking these are images. So images are either, in this case, they have lots of 0 pixels and then lots of bright pixels. Bright pixels are around 255, right? Because it's an 8-bit signals. So it's from 0 to 255. So if I take all your data and I create one huge histogram from all the data, one histogram for all of your data, I get something that looks like this. A lot of pixels are at 0. There's actually a bump here around 255 because a lot of pixels are near saturated, but there are values in between, kind of along the edges. It's kind of hard to see what this looks like, so I'm going to go ahead and take the log of the probability. And now you can kind of see, oh yeah, there's a spike there, there's definitely a spike here. There seems to be a spike in the middle. It's kind of interesting, right? Seems to be a spike around 0. But there is stuff here to model, even though it's relatively small. There are values kind of in between here, okay? But think about this. The output's bounded, right? Goes from 0 to 255. It spends a lot of time either at 0 or at 255. So you definitely want to have, if you have an output, you want that system to produce an output which is going to be mostly 0 or mostly 255. And I said, I know what I can do. I can have you guys scale. So what do? I say y of n, I change the training data, I say y of n is d of n divided by 128 minus 1. So dividing 255 by 128 roughly makes it equal to 2. Subtracting 1 makes it roughly equal to 1. This makes the 0 values go to minus 1. So guess what? These two things correspond to the histograms of the d. This is the histogram of the y. Between 1 and minus 1, right? Now the hyperbolic tangent nonlinearity fits. Does that make sense? It makes sense because guess what? Now my system, and I guess I'll do it here, right? For these values over here, right? My nonlinearity, of course, looks like this. Okay, so this is my up to 1, minus 1. And this is my d, and this is my tan h of d hat. Right, d hat. That's what it is. So that's my nonlinearity. Of course, if I'm above sort of a value here, I'm going to be nearly 1. If I'm down here, I'm going to be nearly, over here I'm going to be nearly minus 1. And kind of, so now it's almost as if I've turned this regression problem, which is a regression problem, into a classification problem, where I'm trying to actually kind of classify, I'm trying to make the outputs decide whether, it's a bright pixel or a dark pixel. But notice it's also continuous, so it'll model that stuff in between too, right? Because I'm not trying to detect whether there's a bright pixel or dark pixel. That's not the goal of this. The goal is to actually model the image. But it's clear that this type of system will do a good job, and if you will, it'll tend to derive output values that will kind of live up here, so there will be a lot of output values. So if I were now to look at kind of the probability density of D2 hat, then it kind of is going to have some energy up here, right? It's going to kind of have some values down over here, and then it's going to kind of have some energy down there, right? But it should be possible to get the input data to drive to these types of densities so that it maps these values to here, and then kind of even gives some values in between. So it should do a good job of approximation. Okay? Now, will it still work if you had a linear? Of course it would, but it may not work as well. Okay? That's the reason why, but by the way, I had to be invasive. I had to go in and actually change my training data so that it fit the nonlinearity that I'm choosing. So these are the sorts of design issues that you have when you're building systems, right? Nobody said, oh, you have to do this. But this sort of mechanism will actually lead to a system which will have a better ability to approximate, and therefore enable you to actually do a better job of actually modeling. Maybe enabling you to have fewer parameters, right? In terms of the number of weights. Certainly I only have 2 layers, so I'm claiming, 2 layers should be enough, right? So this is showing you kind of the design issues around this overall problem. And by the way, like I said, just to make sure that you're aware of it, I know you're doing it this week. Some of you watching it during the week. You actually want to then scale the output back. So once you've estimated your y hat, which is the output of the nonlinearity, so this y hat's tangent of something, tangent of the second layer output, then or second layer linear output, then you add 1. to make it go between 0 and 2, and then you multiply by 128, which undoes this guy. So you need to do that to display it. So when you're displaying your d hats, you want to, and I think I called this d bar. So when you're displaying your d bar, you want to scale it back out and then use that function that I described there. Okay? Any questions on that, at least from the room? You guys understand what you're doing. So the basic idea is there. But that shows you, like I said, there are design issues associated with these problems, and they're almost like data design issues, like what it is that we're trying to do from a standpoint of data processing to be able to get the system to do what we want to do, okay? So that's good. That's actually what we want to do, but that only covers half the problem, right? Or I should say, it only recovers 1/n of the problem, which is the output nonlinearity, right? Everything I just said is all about the output nonlinearity. It doesn't say anything about any hidden nonlinearities or anything like that. So for the output nonlinearity, we have an idea of what to do, okay? Well, for the hidden layers, if you will, hidden layer nonlinearities, of which there are m minus 1 of them, right, for an m-layer system, okay? This is actually open for design, all right? And I know you're saying, what do you mean? Well, choose a function and see how it works. But I'll tell you this, recently, ReLU has become popular, okay? And there's a reason for that, which has to do with the issue associated with other aspects, which we're getting to. This choice appears to provide good performance in a wide range of tasks. And all that means is that, people have then tweaked other parameters to get good performance, right? I mean, there are other things you can choose, number of layers, size, number of outputs per layer, and so on. And if you will, it's both regression, so if you will, modeling like you're doing in the homework, and classification, where you're trying to get, a discrete output to come out, if you will, with respect to the system. And it does not suffer from saturation issues, where such issues cause a weak gradient problem or problems for large scale weights. And what I want to do is kind of decode that issue. And it's actually due to saturation, as I said. So weak gradients, so let me talk about this. Weak gradients due to saturating nonlinearities. That's the issue I want to get into. And the idea here is, if we consider backprop, what we have is the gradient at the mth layer is scaled by this matrix, right? We have this Fm prime d hat n k, and that's this diagonal matrix of derivatives of output nonlinearities. Now, the derivatives are needed because, you know, Fm of D1m, okay? We have Fm prime of D2m and k, and so on, all the way back to Fm prime of D. In this case, at the nth layer, it's L plus 1. Lm plus 1, m and k. These, and of course there's zeros there and there, and of course Fm of d hat is the derivative, sorry, Fm prime is the derivative of Fm of d hat with respect to d hat. Right, that's what that is. If, or say, let, we're using Fm of d hat to be tangent, hyperbolic tangent. Then of course, we plot that out. We know what that looks like. It looks like a saturating nonlinearity. Behaves kind of like this. Is linear, goes to 1. This will go to -1, right? This is d hat, f of d hat, and maybe I'll just leave off the m. That's implied here. So the question is, what's the prime? What's the derivative? Well, f prime of d hat, of course, as you probably know, is secant, hyperbolic secant squared of d hat. And so I can plot that. Okay, I'm going to plot that guy, and there, what I want to do is, well, that's going to be roughly flat here, and it's going to go up and then come back down, right? It's going to look something like that. This is the f prime of d hat, right? Well, if I'm up here, if I'm kind of in this region, okay, there's actually two things wrong. One of the things that's wrong is the secant h squared of d hat is roughly 0. So that means I'm going to be scaling these elements by zeros, or things that are nearly 0. What that's going to do is that's going to cause, so the gradient is scaled to a small value. And so that immediately means that this thing's going to be slow, right? The algorithm's going to end up being slow because I have these outputs being really small, right? Or I should say these terms being small. So it's, you know, the layer previous to this is starting to not have many the updates are going to be numerous, but they're all going to be small value. So it's not going to be able to move the weights very much, okay? There's actually another issue, which is kind of, if you will, the tangent h of d is, you know, approximately 1, so increases in weights are not seen at the output. So the system becomes hard to move, right? Because, what I mean by move, it's hard to move the coefficients because, you know, let's say I want the output to actually change a lot. Well, you know, it's basically going to saturate out, so it's going to be limited. I'll change the weights a lot, and yet the output won't change very much, right? In the sense that the output's going to stay more or less at 1. It's not going to go to 2 or whatever in terms of that because of basically the limits on this. And by the way, you have the same issue down here and down here. Same here. So you have these issues, okay? Now, the reason why we like ReLUs is because if I look at the ReLU nonlinearity, what's that look like? Well, that means that f of d hat is equal to the maximum of 0 and d hat. That looks like, if you will, this guy. I have this, and I guess I want to do it's like this, and it goes up linearly here. So it looks like that. So that's d hat and f of d hat. So now, if I take f prime of d hat, that turns out to be the unit step. So that will be, in this case, also 0. Flat here, but then it goes up to 1. It goes like this. So this is f prime of d hat, okay? So this is non-zero. So basically, these derivatives will either be 1s or 0s, but at least they'll be 1s. And then, of course, so if you will, this this is non-zero f prime of d, which is good. And then the other issue is, of course, so that takes care of 2. Sorry, that takes care of 1, if you will. And 2, you know, f of d hat can be large. So basically, weight changes affect the output. So both of those things are good, right? Both of those things are good. Of course, over here, we could have a problem. Or is it? Basically, that's the question. Is there a problem here? It turns out that it's not clear that it's a problem, whether you actually have this be 0 or not. There actually is a possible change that you could do, and it's called a leaky ReLU. What do I mean by leaky ReLU? Well, again, these are kind of names that people have come up with. The idea here is I have a function which isn't 0 when I'm less than 1. Basically what it is, it's fm of d is equal to the maximum of, I normally would, what did I say? I said 0 and d. I'll make this alpha d hat and d hat, where alpha is greater than, actually it has to be greater than 0 if it's going to actually even exist, and it's less than 1. And so the idea here is I've got a linear function here. So if I'm greater than 0, then it's obviously d hat. If I'm less than 0, then it's alpha d hat, because obviously alpha d hat, you know, is still larger. So this slope, if you will, this slope is 1 to 1. This slope is 1 to alpha, right? And I have d hat and my f of d hat. And then if I look at that derivative, that's going to be 1 and then alpha, right? So I have 1 and alpha as my derivatives. That's my f prime of d hat. So clearly now it's non-zero over here too, right? I got non-zero here, non-zero there. That's all good, right? So I'm able to actually do that. But, you know, the statement I'll make here is that the benefits are unclear. So this is a proposed change, but it's not really clear that you get a huge benefit with respect to this. All right, I think what I need to do here, though, is I have to break this lecture into 2, as you probably know, and we're running out of time in terms of the regular time. So I'll go ahead and pause here and lecture. So thank you very much. We will see you next time.
Sorry.